In this video, we'll continue our discussion of factorial ANOVAs, specifically diving into a bit more about how we actually construct this statistically, creating that ANOVA table, and then moving on to practicing interpretation with some examples and just some extra stuff that didn't really fit anywhere else. So in this particular case, this is an example, but what I really want you to focus on here is the layout. We've got a couple different material types and a couple of different temperatures, and what's important is that we really care about what effects both material and temperature have on the life of a battery. So we aren't just controlling for temperature because we know it's a thing. We're trying to study the effect of temperature on battery life and studying the different materials that batteries are made out of on battery life. And then a supplemental question is we're looking for what choice of material is robust to the different temperatures. So what choice of material is going to give us long life when the temperature is changing? So no matter the different temperatures, is there a better choice among these materials? So that's kind of our goal here. But again, we'll come back to this later. What I want you to focus on in this slide is really the nature of the questions where we're looking at both of these as independent variables that we care about. We're acknowledging that one material may be better than the others on average across these, but that the material type may function differently at different temperatures. And if the material type functions differently, that is, the material type has a different battery life depending on temperature, so one independent variable's relationship with the dependent variable depends on a second independent variable, then we're acknowledging the possibility of an interaction, and that's something that we're going to be studying here as well. Note the layout of the data where we have an independent variable and an independent variable, the different levels, and then we've got 4 replications. So that's little n equals 4 in here. I was explaining this in the previous video. The image is much nicer where we've got factor level 1 for the first factor, factor level 1 for the second factor, and then we've got 4 replications within that join. That doesn't mean that we have 4 replications for factor level 1 for the first factor or factor level 1 for the second factor. It means that when we put both of these together, we've got 4 replications within this set of factor conditions. Now, in general, this is going to be how we're going to construct this, and we can enter our data in several different ways. We'll talk about a few. Typically, the long format where we have column labeled factor A with the different levels, a column labeled factor B with the different levels, and then a column labeled outcome or whatever the outcome is with the different levels of the outcomes, typically how we're going to construct it to be put into R. So we've got factor level B that goes out to little b, factor level A that goes out to little a levels. And then within this combination, you see that this goes up until we get to little n runs within this treatment combination. And again, completely randomized design, so we're randomizing across all of this. Now, when we're constructing this, remember we had the fundamental ANOVA identity that we looked at earlier. This is obviously skipping a lot of work. Please remember that when we look at the B and the N, this is really a triple sum from I equals 1 to A, J equals 1 to B, and K equals 1 to little n. This is a triple sum, but since we only have I as a subscript, these other sums just reduce to their end of their sum. In the same way, this is a triple sum over I, J, and K. All of these actually are triple sums over I, J, and K. So you can just take out the AN, the BN, and the little n and make all of these triple sums. That's where they come from. This is a simplistic form for the textbook. It's simplifying a bit, but honestly, I actually prefer the triple sum because it makes it clearer exactly what's going on in each of these cases. Just like earlier, and this should look very familiar, looking at the average in each of the different levels of factor A and the difference between the grand mean, square that, sum them all up over all of the levels of A, all the levels of B, and all the replications, and that is our sums of squares of A. Do the same thing, except now we're looking at the different factor levels in B. Those factor levels are denoted by the subscript J, so the average of the jth factor level in factor B. minus the grand mean squared, and again add all those up. That's our sums of squares b. You'll note here this term, this one is new. This is our interaction term that kind of falls out. Now this should look very familiar to you. This was our error term actually in the randomized complete block design. We're not going to go too much into the theory. Actually, our last slide today will briefly reference why this is the case. But just be aware of what's going on and why this looks familiar. But in this case, that's going to be our sums of squares a, b, and then the sums of squares error is the difference between the actual observation and our best prediction, which is based on the mean that we saw in I and j. So that's the sums of squares error, and this is going to happen when we have replications. Incidentally, that's the reason why we didn't have this in randomized complete block design. All right, so the degrees of freedom breakdown, we have A levels of factor A, B levels of factor B, and N levels of replications. So our total degrees of freedom is A, B, N minus 1. Just like before, our degrees of freedom for factor level A is A minus 1. Degrees of freedom for factor level B is B minus 1. In this case, again, what was previously our error term is now going to be our interaction term. So the sums or the degrees of freedom for the interaction term is A minus 1, the number of factor levels in A minus 1 times B minus 1. And then the degrees of freedom in the error term is AB times the number of replications minus 1. This should look very familiar to what we had in the original error term in our one-way ANOVA, except now instead of just having A factor levels where we have N minus 1 degrees of freedom within each of those A factor levels, now we have AB factor level combinations, and we have N minus 1 degrees of freedom in each one of those factor level combinations. Our ANOVA table is going to reflect all the information that we just put in. You've got your sums of squares, AB that we just talked about, those degrees of freedom. Then we've got those mean squares calculated exactly like they were before. And now we have the statistical test. So now, remember previously we didn't test in randomized complete block design, we didn't test the blocking factor, but now we care about this. So all of these are tested with reference to this mean squared error. We can test the factor level, or the factor A, factor B, which now we care about, so we do want to run this test, and because this doesn't represent a restriction on randomization, this test is a valid test to run. And the interaction test we can run as well to determine a statistically significant interaction, and remember that guides how we interpret. So we're going to look at JMP Design Expert. Of course, we're also going to look at R, but our textbook uses these, and it's really good for you to see as many softwares as possible. So let's dive into that. The hand calculations, these are here. I'm going to skip over them. You can pause them and use them if you want, but again, I tend to not use these personally. This doesn't work as well for me, especially in R, as just using the other ways. All right, so let's dive into the example. And again, we've got our data, we fit our model, and the very first thing we do is check our assumptions every single time. So look at the normality. Normality looks great. Look at homogeneity of variance. This looks good. This looks good. There's a couple, maybe an outlier down here. Not too worried about it. It's relatively small. We can break these down by the different independent variables. It looks like in the lower levels of temperature and the lower and whatever material one is, there appears to be a little bit more variability, but it's still reasonably close to the other ones. Nothing to be too concerned about. So we're definitely going to keep going with this. Interpreting my output, and we'll have this output, and we'll do the, I think it's JMP is the other one we're going to be looking at too. Or no, this is Design Expert. Okay. So looking at this, we have the overall model significance. So the overall model is explaining variation. We have the significance of factor level A, the significance of factor level B, and the significance of the interaction. Remember, we're not looking at factor level A and B. We start right looking at the interaction. So when I'm looking at this, I start right here. This is the value that I look at to start with. And I ignore everything else. Looking at this, I determine a statistically significant interaction, and so I stop. I don't look at the interpretation of the main effects. I'm not looking, is A effective, is B effective? Because there's a statistically significant interaction, those questions don't make sense. those questions don't make sense. I need to look at the different levels because the effectiveness of A depends, the difference in the factor levels of A depend on the levels of factor B, and the difference in factor levels of B depend on the levels of A. So that's what this interaction means. Remember, first thing I look at after I check my assumptions, it's significant, so I stop and I would go look at that interaction plot. This is the J and P output. This is going to give me the exact same idea, though. I'm going to take a look down in that bottom right-hand corner. I've got material type, I've got temperature, and then I've got the interaction term, material type times temperature, and I'm going to look specifically at this interaction term. I'm going to hyper-focus on that. I'm going to ignore the other stuff. This is statistically significant, so I ignore this other stuff. I don't interpret it. I move straight to that interaction plot. Looking at this interaction plot, I'm looking, so for my questions, I'm looking, does material and temperature have an impact? And so this is going to depend on the different levels. Now, the first thing I'm noticing is that looking at the differences among the different materials, those are the different colors here, these three lines seem to be pretty close at both the low temperature and the high temperature, but I see that in the medium temperature, this black one, this is material 1, seems to take a huge dive down while green and red stay roughly the same. So this is the source of that interaction. I do notice that there's a line crossing over. It's crossing over with a relatively shallow slope, but this definitely could also be a source of interaction where material A3 was worse than material A2 at the lowest temperatures, but material A3 is better than material A2 at the high temperatures, so this is where my interaction is coming from. Again, the reason we can't interpret main effects, something like, is material A3 better or worse than material A2? Well, you can't really give an overall answer to that. It looks like A3 is better if your temperature is medium to high, but if your temperature is low, A2 is better. So there's not an overall answer to what is the best material. That said, it does look like material A1 is worse than the others across all three conditions. Maybe down here in the highest temperature, it looks like it might be better than A2. All right, so that's the answer to my first research question. It definitely appears that temperature has an impact, and it definitely appears that material has an impact, but not always in consistent ways. So we need to look at this graphic. We can't give an overall recommendation of A3 is the best, A2 is the best, whatever. Just based on this, it really depends on the condition. Now, we did have a second question, which is the most robust material? That is kind of across all three conditions, which one stays the most stable? To me, looking at this, it looks like green does. It looks like red definitely takes a tanking as temperature increases, but it looks like green from the lowest temperature to the medium temperature stays relatively the same. And then it has the least drop when it moves from medium to high temperature. Between the green and red. Of course, black has already had a huge drop, so I'm not going to count black there. Black has virtually no change from a medium to high temperature. So in this case, I might say that material 3, A3, might be the most robust material to changes in temperature, addressing that second question. All right, so now let's jump into some random extra stuff that we really don't fit into this, but they were kind of fun, so I figured I'd just toss it in here anyway. First is this qualitative versus quantitative. So remember, quantitative factors are ones that have numbers. Qualitative factors are ones that are more just groups. Qualitative, think favorite color. Quantitative, think 1, 2, 3, 4. In ANOVA, we treat everything as qualitative, but sometimes we do have quantitative factors, and we can use regression models. So I know that I've mentioned this previously, but I wanted to mention this in terms of the interaction too, because we talk about response surfaces and response curves. So when we have a response surface is the three-dimensional way of looking at a two independent variable regression. So this would be our factorial ANOVA with continuous or with quantitative factors if we used a regression framework. I'm just going to call this regression because this is regression. So if we were in regression with two continuous independent variables and a continuous dependent variable, this is what our factorial regression, if you wanted to call it that. It's called multiple regression. This is what our multiple regression looks like when there's no interaction term or very little interaction term. So this right here, when they kind of just nix this interaction term. Now, when there is an interaction term, how an interaction term manifests itself in a regression context is by adding curvature to the plane. So in that flat plane that we saw earlier, that had no interaction term, but now we see a curve going on in this plane. This curve has to do with these different interaction term values. So a small interaction term would have made a very little, not noticeable curve. Here, this interaction term, relatively large, indicates a rather steep curve going on in this particular context. So we can look at a contour plot to help interpret as to what's going on as x1 and x2 change, what's going on with the response, to give us a good idea. In fact, this is what a response surface method you can check out in your textbook does, is it uses the continuous nature of multiple independent variables as well as potential curves involved with those variables and their interaction terms to attempt to predict what the best case of the outcome would be. So in this particular case, let's say we wanted an outcome that was as high as possible. We might be looking for a high value of x1 and a high value of x2, and we might continue doing more and more studies at higher and higher values of x1 and x2 as much as are feasible to see if this pattern continues out. That's actually the whole idea behind a response surface design. Real quick, as we dive into an extension here, you can absolutely have more than two factors. It does get a little bit more complicated. In fact, it gets a lot more complicated. Those ANOVA tables and the sums of squares become a lot more difficult. But as we dive into this, we can have different letters. So let's say C is our third factor. Note that our two-way interactions can now be between A or B or C. So we can have an interaction with A and B just like we had before, but now we could have another two-way interaction between A and C. We can also have a three-way interaction between A and B and C, and there's an example in your text to dive into this a little more if you're interested in doing so. So finally, one thing to consider is the factorial ANOVA with a sample size of 1. So think about, if you go back to the ANOVA table, just think about those degrees of freedom. I'm not going to demonstrate this here, but it's very easily demonstrated as to why a factorial ANOVA with a little n of 1 breaks down, and think about how that could cause problems practically when calculating the MSE. And again, just go back and do a little quick calculation and you'll quickly see why that is. So in this case, because of the problems with the error, we then use the highest level interaction term as our error term. In fact, this is what happened in randomized complete block design when we just had one replication as a rule. So when we do this, we assume that there is no highest level interaction. We treat the highest level interaction as error, and then we assume that there was never a highest level interaction term, that was always just representing error. This is called the idea of additivity when in the two-way ANOVA case. When our highest level interaction is our only interaction, an additive model just means that we don't have any interaction terms in it. So this assumes this additive model. There are definitely ways that we can check on this assumption, even when we just have a sample size of 1 that you can dive into, but we won't have time to go into it here. So this has been a quick presentation of how we implement a factorial ANOVA, specifically focusing on two-way ANOVAs, how we can construct the different sums of squares, how we look at the degrees of freedom, how we construct the ANOVA table, and then how we can go through with an interpretation in a case where an interaction term is significant. As well as just a few random other things that our textbook mentioned, and then a couple things that our textbook doesn't mention but I find interesting. In the next video, we'll get to dive into an R case, exploring how we implement a factorial ANOVA in R.